Good day, everyone. Today I'm going to show one example of the root finding problem and solve it by using the Halley's method. So today we are giving the root finding problem of the fx is equal to x power 4 minus 2x cubed and minus 4x squared plus 4x plus 4. So the question one is want us to show that there is a real root between the interval 1 and 2. So according to this theorem, if fa times fb is less than 0, so there is a root between the a and b. So we first find out what is f1 inside this fx, the value of f1. Four square times 4 plus 4. So this is our FA. So our FB is F2. Our FB is 1. We sub into 2. So we get negative 4. So we can conclude that um, since F1 times F2 is less than 0, therefore we can conclude that there is a real root between interval 1 and 2. Okay, so our first question is done. Okay, continue. The second question. Second question want us to determine the number of iteration that necessary to solve the root finding problem by using the Halley's method with the accuracy of 10 power of negative 5, and then use this as the stopping criteria, and all result is solved in 7 decimal places. So in order to apply the Halley's method, right, so this is the formula of the Halley's method. So in this formula we need to find the first derivation of the fx, and then we need to find the second derivation of the fx. So this is our first derivation of the root finding problem and the second derivation. And then we sub this derivation into the Halley's method, and we replace the x into the xn minus 1. So this is what we get after substituting the x to x minus 1. This is our Halley's method formula. And then before we start apply the Halley's method, we need to find the initial approximation root. Or so it is our x naught. So we use the midpoint rule to find our initial approximation root. So we apply a plus b divided by 2. So our a is 1 and our b is 2, and then it's divided by 2, and then we get the initial root with 1.5. And then we can start doing the Halley's method table. So this is our n, this is our xn, our approximation root, and then this is our stopping criteria. So when n is equal to 0, our initial problem is 1.500. Yeah, and then this is no, right? So put NA here. So when n is equal to 1, so we substitute our n into this equation, Halley's method equation. So we substitute um, our 1 into here, so it's equal to x naught. Okay, so can type here x naught is this one, x naught 1.5. Okay, we minus 2 times 4 times x naught power 3. Okay, then we minus 6 times x naught square. Here we put one more bracket. This one x naught copy down. Then we minus 8 times x naught plus 4. Okay, close bracket. Then we times this one, x naught power 4. X naught power 4. Then we minus 2 times x naught cube minus 4 times x naught square, and then we plus 4 times x naught and then plus 4. Okay, close bracket, and then it's divided by this one, right? So we can just copy down this 2 times, okay, copy down this 2 times x naught square minus x naught plus 4. Okay, then this one got another bracket because we need to square it. Okay, then close the bracket. This one we put one more bracket. Okay, then we minus 12 minus 12 times x naught square. Oops, sorry. Times x naught square. Okay, and then we minus 12 x naught. 12 times x naught. Then minus 8. Close bracket. This one is times with x naught power of 4. Then minus 2 times x naught square, and then minus 4 times x naught. Sorry, I think I did wrongly in here. It's supposed to be cube, and that's minus 4x square, and then plus 4x plus 4 plus 4 x naught plus 4. Okay, close bracket, then close one more bracket. So we get our first value is 1.414521.6. Okay, Actually, we can write the round round this whole term round this whole term into 7 digit. Okay, so we get our first term is 1.4145216. Then can calculate our stopping criteria. So it is equal to this cell minus x1 minus x0. Okay, you can put the absolute here. Okay, so we always get the positive value here. So this one we drag down, we get 1.136. Okay, so this is not meant the 10 to the power of negative 5. This is 10 to the power of negative. Since we doesn't met our stopping criteria, so we continue to another iteration. So this one we drag down. Okay, so our root is, so we found that the third iteration is same with the second one, so this is 0. Okay, so we can conclude that um, the root um, of this root finding problem um, in interval in interval 1 and 2 has a um, in the interval 1 and 2, okay, is approximated as x3 equal to 1.4142136, which is accurate to at least within 10 to the power of negative 5. So okay, so our question 2 is done. So we only use 3 iteration only to solve this root finding problem. Okay, so we continue to our third question. So it's given that the actual root is given by the x is equal to 1.414213562373710. Okay, so he wants us to find the relative error in part 2 and then determine the number of significance of the digit. So our relative error formula is x of the exact value minus our approximation value and divided by the exact value. So our relative error is equal to our exact value minus the approximation value. So our exact value is 1.414213562373710. Okay, copy down this value. Okay, put here. So is the, you see this bar, right? So it's absolute of the exact value minus our approximation value. Then we divide by absolute value of the exact value. Okay, so we get 2.66 times 10 to the negative 8. So in order to find the significant digit, we need to find our p-value. So since 2.66 is less than 5, right? So our t is taken as 8. So you can write conclusion that um, the relative error of Halley's method is 2.6606 times 10 to the power of negative 8 with 8 significant digit, which is accurate, um, which is considered as very accurate to the real root. Okay, so actually we get x significant digit. This means that the smaller of the relative error indicate that there's a higher accuracy to the actual value. Okay, I think that's all for our group demo for solving the root finding problem by using the Halley's method. Okay, thank you for your watching. Bye bye.